Oh, hey, here's the day 10 homework. Starting with number one. All right. So there's options. There's options on how to do this problem. Why don't I maybe do the most obvious way first? The most obvious way to do it is to apply quotient rule to combine these two logs. So it becomes log base 7 of x cubed plus 27 over x plus 3 equals 2. And then from here, if you have just a single log equals just a constant, then you can just convert this down to exponential notation. If the log base 7 of this stuff equals 2, then that means you keep that base, raise it to the power of 2, and that would have to equal the stuff. And so the logs are gone now simply because we converted to exponential notation. All right. Now, a different way to think about this, and in my opinion, a worse way, is just to kind of think, all right, well, I know if I have log base 7 of some argument equals log base 7 of some argument, I can definitely kill the log base 7s. So what is 2 as a log with a base of 7? Well, wouldn't it be the log base 7 of 49? And so the second you go here, where you have log equals log, then we know at that point we can kill the logs using exponentiation. And then we get, again, the x cubed plus 27 over x plus 3. And it equals 49. So we're landing in the exact same spot because, again, remember, if this was a 2, we could just convert to exponential notation, saying 7 squared equals this stuff, 7 squared being 49. So either way you slice it, we're landing here. And what the heck do I do from here? Well, again, you got two choices. Are you recognizing that this is a sum of cubes? That actually is factorable. And when you factor it, you will get x plus 3 as a factor, and it will cancel. So you could do that. And I recommend you do, because you don't want to have a cubic function. Cubic functions are harder to deal with. So remember to factor a different or a sum of cubes. It's going to factor down to be the cube root of this, which is just x to the 1, and the cube root of that, which is 3. Then it's going to be that cube root squared, so x squared. On the end, it'll be this cube root squared, so 9. And in the middle, it'll be the product of those two things. So 3 times x is 3x. And then remember, we had an acronym for the sign pattern, SOAP, SOAP, telling us that our 3 signs were the same sign, the opposite sign, and then always a plus sign. So if we are factoring a sum, then the same sign is a sum. The opposite sign is subtraction. And of course, always plus is always a plus. So there's our factored numerator. Then in our denominator, we've got this x plus 3. And those guys are going to cancel, slash, slash. And the whole thing equals 49. So now you've just got an x squared minus 3x plus 9. That equals 49. So subtract 49 from both sides. And you've now got an x squared minus 3x minus 40. So is that factorable? Are there factors of 40 that will give 3? I don't know. Let's find out. Negative 40, 4 and 10. Those have a sum of 6, so that ain't happening. 5 and 8. Yep, there it is. We're factorable. So x. My other monitor just changed. It was weird. It freaked me out. Train of thought lost. Minus 5 plus 8. Nope, completely wrong. I played myself. That should be positive. That should be negative. So it's minus 8, obviously, and an x plus 5. Which means I get two solutions. I get an x that equals 8 and I get an x that equals -5. And here, we're done. These are our solutions. So we didn't make a u substitution. We don't have to go back and take the ln of anything or the log base anything of whatever. The only thing we do have to do is just check to make sure that those values work in our original expressions. And I'm not saying you have to check it all the way, but you certainly want to at least check to see if any of them generate negative inputs in a log, because then they would certainly be extraneous. Another thing to be aware of is we just canceled out an x plus 3. So if we happen to get a -3 presented to us, that would be extraneous as well, because, you know, it got canceled out. So the -5 is suspect. And indeed, if we plugged in -5 here, we would get -2, and that would be undefined. If we plugged in -5 here, yeah, -5 cubed is still negative, so this would be negative as well. So both of those are undefined at that value. So that guy is undefined and needs to therefore be discarded. I didn't check the 8, but I bet he's fine. 8 is clearly going to give us a positive and a positive. Now the question of, is it really right or not? Honestly, I don't care. I assume I did the math right. Y'all could check it if you want. Figure out what 8 cubed is, add 27 to it, divide it by 11. See if you get 49, because if you do, log base 7 of 49 is going to be 2. But I'm done, and I'm happy, except for giving my answer in sat notation. I'm getting 8 and nothing else. Moving on. Okay, this nightmare. So we said before we can do anything, we definitely need to condense our logs. I can't do anything when I've got 1, 2, 3, 4, 5 separate logs. If I could boil this down to log of x equals a single log of whatever it is, then I know at that point I can cancel the logs. But you certainly can't cancel the logs now. And that's what people sometimes try to do. They kill the logs too soon. And I don't know what they do, but you can't do it. So we got to combine the logs first. So, oh boy. Great. The left-hand side is fine. And over here, what are we going to do? We got to work from the inside of the brackets out. So I'll take it fairly slow, because maybe some of you guys have forgotten how to do this mess. It was a while ago after all. This is going to be, you pull in the 2, so it'll be the log of 64. You pull in the 6. I don't know what 3 to the 6 is. It's probably big, but not too big. 729. But then it's going to be 729 times the 64. Not loving this. I don't think I want to write it the way it is. I'm going to try to be smart about this if I can. At the risk of losing you, 8 squared is 64. 8 squared is 64. That's true. No one's going to deny that. But you know what else 8 is? That's a 2 cubed. So 8 squared is a 2 cubed squared. So it's really just 2 to the 6. I think I want to express it as 2 to the 6th. We'll see. Maybe I don't. And then this guy here, that's just going to be 3 to the 6th. Bracket. This is going to be log of 4, bring in the 2. This is going to be log of 3. I don't know. While I'm working with powers of 2, maybe I want that to be a power of 2. Just leave it as 2 squared instead of 4. For now, no reason not to. Okay. So finally, this is going to kind of pay off for us, because you guys know that a to the m times a to the n becomes a to the m plus n, but slightly less well known than that might be a to the m times b to the m. Well, that is going to be a times b to the m. So slightly different variations on similar rules. So what I'm getting at here is we are about to multiply these. So this will be a third of a single log of 2 to the 6 times 3 to the 6. Well, because the powers are the same, you can think of that as 2 times 3 all to the 6. So this is going to be 6 to the 6th. And again, I don't know what that is. I don't need to simplify it though. Leaving it as 6 to the 6th is great, especially when we're about to pull in a third as a power. And it's really just going to be 6 squared. So I never really did have to evaluate any of these out. And if I did evaluate them out, it would have been worse for us. It would have been big numbers that were hard to deal with. So just leaving them in their exponential form was better. I'm going to keep leaving these alone too. This is log of 2 squared plus log of 3. Log of x. So like I said, once I pull that in, it's going to become log of 6 squared. I think I am ready to go ahead and just call that a 36. So it'll be 6 squared for 36. I am ready to just call that a 4. And since it's minus, that'll be a 4 in my denominator. This is plus, so that'll be a 3 in my numerator. And then guess what? 36 divided by 4 is 9. 9 times 3 is 27. So you're looking at a log base 10 of x, which is equal to a log base 10 of 27. And basically now, again, remember the math that's happening technically is we have an understood base of 10. So you exponentiate, meaning you make these things powers on a common base of 10, and then these cancel, and you just land on x equals 27, and you're done. There's your answer, 27. That's kind of a weird one. Okay, moving on. So 3. So this is subtraction, which means we'd have to do quotient rule, which means I'd have a linear divided by a quadratic. There's nothing wrong with that. We could do it. I've got a different idea though, but I don't love it. I think we spoke in class about how we could push these terms around before dealing with them. So log base 3 of 2x minus 5, I'm happy with. But I want to boot this guy to the other side. And then this negative 2, I'm going to bring him back over. So if by adding 2 to both sides, I'll go plus 2. I'll add this whole log expression to the other side. I'll get log base 3 of x squared plus 4x plus 4. And so I can't cancel the logs yet because of this pesky 2, but that's when you realize that a 2 can be re-expressed as a log with a base of 3, as long as you're taking the log base 3 of 9. That's a very fancy way to just write the number 2. So suddenly now I've got log base 3 of a 2x minus 5 plus a log base 3 of 9. I can just use product rule now to combine those logs. And I'll have log base 3 of 18x minus 45. And of course, over here on the other side, there's nothing happening. This guy's just going to come along for the ride. Log base 3 of x squared plus 4x plus 4. This expression is just patiently waiting for the other one to become a simple log base 3 of an expression. Because finally we've arrived at the point where we have log base 3 of stuff equals log base 3 of stuff. And now we can get rid of the logs. Again, we're exponentiating. We're going 3 to the power of this equals 3 to the power of that. So then the log base 3's would cancel, giving me the 18x minus 45 equals x squared plus 4x plus 4. And then I just attack this like a regular old quadratic. Subtract 18x from both sides, add 45 to both sides, landing on an x squared minus 14x. And we're adding that, so plus 49. Okay, so that's easily factored. We get x minus 7. And then another x minus 7. So it's just x minus 7 quantity squared. So that means we have one solution, and that solution is positive 7. And that solution just happens to have a multiplicity of 2. Remember we talked about multiplicity, meaning that that solution happens to occur twice. But even when you go to write your solution set, it's not like you're going to say it's a set containing 7 and also another 7. Sets never have the same element in them twice. So even though the 7 may occur as a solution twice, you'd still list it in your set only once. And oh, by the way, I shouldn't be writing it down. This is premature because we didn't check to see if it was extraneous. So what if I plugged it in up here? 14 minus 5, well, that's positive. 49 plus 28 plus 4, that's positive. So we're fine. It's not extraneous. It is our solution, and we're done. Did I take a weird approach to this problem? Maybe. Do you want to see a different approach to this problem? You probably don't, but you know what? If you don't, then fast forward because I'm doing it. What am I looking for? Little Dotty boy. All right, so Dotty boy. I'm going to do the problem a separate way over here. Copy, paste. Yoink. Shrink. Okay. Grow. Not good. I know the trick. Make it super wide. 2000 wide. That'll work. Okay. So let's do it a different way. And by different way, just do it the way it was given instead of adding this to the other side and adding the 2 and farting around with it like that. Just go ahead and do what maybe is the more obvious thing. Take the 2x minus 5, put it in your numerator. It's quotient rule, so take the x squared plus 4x plus 4, put it in your denominator. Let the whole thing be equal to -2. That's fine. What you have now is different. Instead of like what we had over here where we had log equals log and we canceled the logs, we have a single log that equals a constant, and that's just as good. We can still get rid of the log by converting to exponential form. We know that log base 3 of this expression being equal to -2 means that 3 to the power of -2 is equal to this expression. And 3 to the -2 is, of course, 1/3 squared, which is 1/9. So you probably want to think of it like that. Forget that. So basically, I did all that work over here to avoid ending up with a rational equation. But we studied rational equations. You guys know how to deal with them. How come this slider does nothing? Does that make any sense to anybody? That I slide the slider and nothing changes? That's pretty cool. 100% view doesn't even fit. 50% view. I'm trying to say, over here, I finagled all this junk at the beginning so that when I finally did kill the logs, I have a polynomial equation. It's just a quadratic. And so maybe from there, it's a little easier to solve. By not doing all that stuff, by the time I get rid of the log, I'm looking at a more complicated equation. It's a rational equation. But listen, we studied those. They're not hard. You guys know what to do. You just multiply through by the LCD. Or not even that. You just cross multiply. There's nothing wrong with thinking about it like that. So, you know, if you're going to multiply by the LCD, you'd literally be multiplying through by a 9 times an x squared plus a 4x plus a 4. And when you multiply through by that, guess what? These things cancel and you multiply through by 9, getting your 18x minus 5. Here the 9 cancels, and so you just end up getting the x squared plus 4x plus 4. But we're already in the same place now. We've met up with our previous one. And actually, this seems to have maybe gotten us there faster, right? But we are now at literally, okay, that's 45, obviously. Erase, erase, erase. Somebody forgot to distribute the 9 onto the 5. So 45. Now I can say we are literally at the exact same spot where we have this polynomial now that we solve. So I'm not going to continue on, obviously. You guys can see the different approaches, and you may take either approach, whichever one resonates with you, whichever one feels more logical. Go ahead and do it, okay? Now let's go to 4. 4 is looking weird. 100% view is looking weird. 150% view is looking weird. Best fit's looking okay. All right. This seems the same. You could do the same old stuff. I would say that I think method 2 is the better method. Just go ahead and do the quotient, because who cares? This will become log base 3 of a 2x squared all over a 5x minus 9. It'll equal a 1. And then just convert to exponential form. This will become a 3 to the power of 1, and it'll be equal to this argument, 2x squared minus 5x minus 9. So you cross multiply. 15x minus 27 equals 2x squared. And then that's a quadratic. So subtract the 15, add the 27, get this thing in standard form. You got a 2x squared minus 15x plus 27. And of course, you're wondering if this thing's factorable. So you do the AC method. You get 54. You're looking for factors of that make negative 15. It's obviously negative 6 and negative 9. Right. Yeah. Okay. So you factor by the quote unquote guess and check method. Although if you've been practicing your guess and check method, you're not really guessing. You know exactly what you have to do. You want these values. So you put a 2x, you put an x. You want a negative 6, you better put a negative 3 right there. You want a negative 9, you put a negative 9 right there. I'm not guessing and checking. That's it. I know that's it. I've been calling it the guess and check method, but I was just kidding. All right, so now what? You pull out your solutions. This guy gives me a 0 at positive 9 halves. This guy gives me a 0 at positive 3. So they certainly seem like they're probably both going to be real and legitimate solutions, but you got to check. You never know. For example, if I got an answer of x equals 1, he seems great. He's positive, but no, he would fail up here because 5 minus 9 would be negative, right? It is possible to get a positive x value that when you plug it in causes you to be taking the log of a thing that's negative. So it's not right to just think that negative x's are bad and positive x's are good. You have to actually plug them in and test them. But I think we're okay. Plugging in 3 gives 15 minus 9, and that's big enough. And 9 halves is bigger than 3. That's 4.5. So 5 times 9 halves is big. Take away 9 is positive. And here, x squared is always positive. Times a positive is always positive. So neither of those fail in that log expression. So they're both our solutions. So we express our solution set then in numerical order, 3 being the smaller, 9 halves being the bigger. Put a box around it. And boy, am I proud of us. That's 4. And it looks like there's 4 more. So on we go. So this looks different. Okay, whatever. So I'm looking at exponential expressions that all have different bases. So that's concerning. But no, it isn't, because I'm sure you all recognized pretty quickly that all of those bases can be expressed as powers of 2. So if we just rewrite all of these guys with that common base, then the rest should be cake. 2 to the x will just stay 2 to the x. 16 is a 2 to the 4. So that's a 2 to the 4 to the 3. Which of course will just be 2 to the 12th, but I'll do that in a second step. Now this one seems more complicated, but it's not. It's just going to be 2 squared to the 5. First of all, I don't know what Joker did this, but log base 5 of 5, that's just 1, right? So just evaluate that. So 5 times log base 5 of 5, that's just 5. So I'm not even going to mess around with that anymore. That's gone. That's stupid. I don't know why it was ever there. But that means we're now looking at what? A 2 to the 12 times x. So that's technically 2 to the x plus 12. Oh, that's a 2. I can sneak a 1 in there. Because we're doing power times a power. You would add the powers. This is power to a power. So you multiply to get 2 to the 12. But then this is power times a power. So you add the exponents. And then the whole mess equals 2 to the 10. So guess what? At this point, you can kill the 2's. How do you kill the 2's? You're really taking the log base 2 of both sides. But that has the effect of essentially killing the 2's. So you just get the exponent, the x plus 12, and you get the exponent 10. And then you take away 12 and you get negative 2. All right, can I have a negative? Sure. This is not a log equation, it's an exponential. So x was always happy to accept a negative input anyway. It would just be the reciprocal. So that negative 2 is our one and only solution. I'll express it in set notation because that's my preference. So give me that. I think I'm done. I don't think there's anything more to say there. So I hope you followed it. Moving on. Another one of these. All right, again, you got your choices. If you want to just tackle it the way it's written, then you'll combine all these into a log base 5, where you've got an x minus 1 in your numerator, an x minus 2 in your numerator, but then this is minus, so you'll get an x plus 6 in your denominator, and then the whole thing equals 0. Okay, so from here you can still convert to exponential notation. You just go 5 to the 0 and set it equal to this whole mess. X minus 1, x minus 2, x plus 6 all over, parentheses, 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 parentheses. Okay, guess what 5 to the 0 is? It's just 1. And guess how you would solve this? You could just cross multiply. I do want to expand this out when I cross multiply because I want to get it into an expanded polynomial where I can combine like terms and all that. So expand this out. X squared minus 3x plus 2 equals x plus 6. So subtract, subtract. You now have x squared minus 4x minus 4 equals 0. This guy is factorable? No, no, he's not. No, he's not. So, okay, whatever. I guess it's back to quadratic formula. So x equals negative b plus or minus the square root of b squared minus 4ac. 4ac is actually going to be 16, so it's plus 16 all over 2a, which is just 2. All right, so 16 plus 16 is 32, but obviously that's 16 times 2. 16 plus 16 is 16 times 2. Square root of 16 is 4, so this is 4 root 2 all over 2. So x is equal to 2 plus or minus 2 root 2. It's a lot of 2's. Okay, cool. How do I check for those being extraneous? Well, 2 root 2 is clearly bigger than 2. So 2 minus 2 root 2 is clearly negative. And then a negative thing, take away even more, is more negative. So the minus version definitely fails for us. Now, what is 2 plus 2 root 2? Can you rest assured that it's bigger than 2? Yeah, certainly. Is it bigger than 1? Certainly. So I don't know what this is, but it's bigger than 2. And so it's certainly positive here because a positive plus a thing is positive. Here, a positive thing bigger than 2 minus 2 is going to stay positive. It's going to be positive. So that guy is fine. He is our solution. So x is an element of the set that contains 2 plus 2 root 2. Okay, I'm pausing a little because there's something I'm afraid I'm kind of glazing over. So this maybe is just another one of those moments where if y'all don't give a damn, you can fast forward. But there's something here I should probably be addressing, kind of. Cheryl. You may or may not remember, back when we were doing rational inequalities, I told you that from this moment right here, it really was not okay to just cross multiply. Really what you were supposed to do was expand this bad boy out to get x squared minus 3x plus 2 all over x plus 6. You were supposed to actually take the 1, subtract it from both sides. So say minus 1, and get the whole thing equal to 0. So the 1 could be re-expressed as x plus 6 over x plus 6. I don't really need to worry about that here, though. This negative would distribute. We would get what? X squared minus 3x minus x is minus 4x. Positive 2 minus 6 is minus 4 all over x minus 6. The reason why we weren't really allowed to cross multiply here is because back when we were doing polynomial inequalities, we didn't want just the zeros. We wanted the points of discontinuity as well. So x equals 6 would have been a point of interest for us. But over here, x equals 6 was always just going to be sort of an extraneous solution anyway, like it wouldn't really work. So losing that value was never going to be a big deal. So long story made short, you don't really need to worry about that in the setting that we're in right now. It's fine to just kind of cross multiply through by the LCD, however you want to think about it. You'll get the answers you need. Okay, great. Okay, I just paused for a second because something felt weird. I don't know. It's 12:30 at night. Maybe I'm getting tired, but that plus is supposed to still be a plus. So all that chit chat about 6 really should have been chit chat about a negative 6. But even still, negative 6 is even worse than 6 because clearly negative 6 gives us 0. It gives us a negative. Negative 6, if it did come up as a solution, clearly would be an extraneous solution. So we're not missing anything by just cross multiplying in the first place and solving and getting the real solutions. So you may promptly forget everything I said and move on. What we did over here was A-okay. Let's talk about 7. What? How do I do this? Okay, so here's a problem that's a little different. Let's see what we should do. Okay, I paused the recording again so I could think for a second. You know, obviously I'm just having a brain fart. We've been doing this a whole bunch of times. Remember when we would get to the point of log base 3 of x plus 1 equals log base 3 of x times x minus 7 or whatever. I've been telling you that at this point, you could just cancel the logs. And I've been reminding you that the reason why we can cancel the logs is because what we're really doing is exponentiating. Well, that little rule is coming home to roost in this problem. They're now giving you 4 to the power of the log base 4 of stuff. Shouldn't 4 to the power of the log base 4 cancel like we've had it cancel over here? It might be time to write this rule out more generically. If you have some base of an exponential being raised to the power of a log of that same base, then whatever's in your parentheses, some function of x, f of x, all that mess is going to cancel. The b to the log base b is gone. This whole thing would just be whatever that function is in your parentheses, whatever that argument is, everything would cancel. You would just get that, right? So taking that idea and running with it, this is another kind of silly problem where everything just cancels and you very quickly just land on an easy to work with polynomial equation. So I'm going to put this in the corner, put this in the garbage, erase. And based on everything I just said, it is perfectly safe for you to just imagine these canceling. This whole expression will just be 2x squared. This whole expression will just be x. And this whole expression will just be 15. And lo and behold, this seemingly exponential function involving logs, it's not, it's just a quadratic, and it becomes a quadratic in one step. So from here, we just work it. This is going to be 2x squared plus x minus 15 equals 0. So I'm wondering, hey, there wouldn't happen to be any factors of negative 30 that add up to 1, are there? Let's see. Negative 1 and 30? No. Negative 2 and 15? No. Negative 3 and 10? No. Negative 4 and there isn't anything? Negative 5 and 6. Got it. So anyway, for you bad factorers out there, this is your method here. Just start at 1 and keep going up by 1 until you either find it or don't find it. By the way, if this thing wasn't factorable, this would be your clue. By the time the two factors kind of close in on one another, obviously after negative 5, you're not going to try negative 6 again and 5. At that point, you're just circling around, right? So at this point, when the two factors zero in on each other, you know that you've tested every possible option. And if none of them worked, that's the moment when you could safely say that this guy just is not factorable, and you'd have to use the quadratic formula. That makes sense? That's kind of important. All right, hey, guess what? I don't need the quadratic formula because this is factorable. I'll huck a 2x right there. I'll chuck a x right there. And I'll try to get a positive 6 and a negative 5. I've already got a 2, so I'll put a plus 3 right here, generating 6x as my outer product. You want a negative 5? Well, stick a negative 5 right here. And now you have an inner product of negative 5. And we're done and we're factored. I shouldn't have said we're done. We're not done. We're done with factoring. But what are my solutions? Well, this factor gives me a 0 at 5 halves. This factor gives me a 0 at negative 3. Anybody extraneous? Let's find out. This negative 3 looks suspect. It is, because it fails here, of course, immediately. This guy will not accept negative inputs. He won't even accept 0 as an input. Now, the negative 3 would have been fine here, but not here. So it's extraneous. What about 5 halves? It's fine here. It's fine here. So it's fine. That's going to be our one solution. Make sure you do test all of them, because it is completely possible for both solutions to be extraneous and for you to have an equation that just has no solution. I spelled solution wrong. No solution. That can happen. So make sure you're vigilant in testing both. Okay, pretty proud of that problem. Let's go and do the last one. Number 8. This doesn't look bad. Just combine your logs like we've been doing. This will be a log base 2 of, now it's 2w plus 1 and 2w minus 1. So you probably just want to expand that out. It would be 4w squared. And of course, you'd get negative 2w and positive 2w in the middle. So the middle terms would cancel and you just get minus 1. It's a difference of squares. On the other side, power rule says pull that in first. This is now a 9. And then product rule says you're working with log base 2 of a 99. At which point, via exponentiation, if I just make that a power on 2, if I make this a power on 2, then again, these cancel, and I just get my 4w squared minus 1. And this, of course, cancels, and I just get 99. And then this solves very easily. It's not even a factoring problem. You're just going to add the 1 to both sides. Those cancel. You now have a 4w squared that equals 100. You'll divide by 4 and get a w squared that equals 25. Now you'll take the square root of both sides, remembering, of course, to generate a positive root and a negative root. Even though the negative one's probably extraneous, right? You still got to remember to at least generate it. Don't let your algebra skills go down the tubes. And oh, look, if I plug in a negative, I do get a negative, and that's undefined. And so, okay, fine. So if you forgot that you should have a positive and a negative root, it really kind of wouldn't hurt you, because it does turn out that he's extraneous and he should not be in our solution set anyway. What about the 5? Is he fine? 11's fine. 9 is fine, and everything's fine. So yes, the positive 5 is our one and only solution. Thus concludes Mr. F's video of the day 10 homework. Okay, great. See you guys.